Hello, and welcome to the TI Precision Lab covering component selection for SAR ADCs. In this video, we cover the mathematical algorithm used in the SAR drive calculator used to select the R and C values in the charge bucket. This video goes into the math behind the SAR drive calculator used in step 3 of the process for selecting the external components for a SAR ADC. In this video, we will cover the mathematical algorithm used in the calculator to find the amplifier bandwidth, as well as the range for the RC circuit. Before going through the derivations, we will introduce the overall assumptions and objective of the algorithm. The assumptions are based on measured and simulated results for multiple designs. There is a significant amount of technical literature covering the selection of the amplifier and RC charge bucket circuit, and most of this literature will use similar approaches. We believe that this approach combines the best aspects of these methods and provides a more methodical way to optimize the circuit. One assumption is that the input is a full-scale input. This will have worst-case settling. Another assumption is that half of the charge of the sample and hold capacitor is delivered from the amplifier and half is from the external charge bucket capacitor. Also, the droop after the acquisition switch is closed is assumed to be 100 millivolts. The error target here is 1/2 of an LSB, and the amplifier RC circuit is assumed to be a second-order system. Finally, we assume that the amplifier is 4 times faster than the RC charge bucket circuit. Many of these assumptions are based on observation from many measured and simulated circuits. The assumptions aren't perfect and will not always be completely accurate. However, they will allow us to develop a set of equations that provide component values for SPICE optimization. First, let's determine how to select the external charge bucket capacitor C-FILT. Equation 1 is the standard equation for capacitor charge applied at the end of the acquisition period. That is, charge on CSH is the full-scale voltage times the sample and hold capacitance. Equation 2 lets us know that the total charge delivered to the internal sample and hold capacitor is from the amplifier and the filter capacitor. Equation 3 indicates that half of the charge delivered to the internal sample and hold capacitor is from the external filter. Equation 4 combines equations 1 and 3. Equation 5 applies the general relationship for charge so that we can consider the droop in filter voltage. Equation 6 combines equations 4 and 5. Now, we have a general equation for the filter capacitance based on the internal sample and hold capacitance. In the next slide, we will simplify this equation by applying specific conditions to it. Here again, we repeat the general equation relating C-FILT to CSH. Now we make some assumptions for a typical ADC system. That is, the full-scale range is 4 volts, and the droop on the external filter capacitor is 100 millivolts. Substituting these conditions, we get the relationship that C-FILT is 20 times the internal sample and hold capacitor. This relationship has been used in many design examples and has proven to be accurate for most cases. In some unusual cases, a different C-FILT is required for better settling. For that reason, the algorithm provides alternative minimum and maximum values for the external filter capacitor as given in equations 8 and 9. The next set of equations relate to the time constant for the amplifier and RC load. Equation 10 is for the filter charge during the acquisition period. Note that tau c is for the complete time constant and is partly from the amplifier bandwidth limitations and also from the RC circuit. Equation 11 states that the final error is less than half of 1 LSB. Equation 12 states that the droop at the start of acquisition is equal to 100 millivolts. Equation 13 is determined by substituting the 3 previous equations, and equation 14 solves for the time constant. This is the final slide in the derivations. Equation 15 is a general equation for adding time constants. The RC time constant and op-amp time constant add like the square root sum of the squares. As a rule of thumb, we have found that the amplifier bandwidth should be 4 times faster than the RC bandwidth. Substituting equation 16 into equation 15 and solving produces equation 18, which relates the op-amp time constant to the total time constant. The same approach is followed to find the time constant for the RC circuit. This is used in equation 20 to find the nominal resistance used in the external charge bucket circuit. Experience has shown us that the optimal value for the filter resistor may be different than this nominal value, so we set up a range of 1/4 the nominal value to double the nominal value. This range is used in simulation to optimize the filter setting. Finally, equation 23 determines the minimum unity gain bandwidth for the amplifier to achieve good settling. That concludes this video. Thank you for watching. Please try the quiz to check your understanding of this video's content.